Hello students, welcome to 7 classes. So in this video, we are going to start the chemical kinetics. Okay, this is a very important chapter and a number of questions they are asked from this part, that is chemical kinetics. See what chemical kinetics is about. It is about understanding the rate of the reaction. Okay, let's suppose a chemical reaction is happening. This is a reactant which is converting into the product. Okay. Now, in this chemical reaction, the reactant at which speed is converting into the product, what is the rate of that reaction, that is studied in the chemical kinetics. Okay, so it deals with the rate of the reaction by which speed the reaction is happening. Okay, we will understand that how do we represent it very easily. Okay, very simple topic is it. Now, suppose this reaction is happening. Okay, now at time t1 the concentration is r1. Okay, and at time t1, at the same time t1, the concentration of product is p1. I can write it like this, right? And at time t2 the concentration of reactant will be different, which I can write as r2, and the concentration of product will be different, which I can write as P2. Okay, so change, how do we write the change? Delta T is equal to T2 minus T1, and delta P represents change in the concentration of the product, that is P2 minus P1, and delta R, that represents change in the concentration of a reactant, that is R2 minus R1. Okay, in this way we represent it. What is P2, P1, R2, R1? That is the different concentration of a reactant and product at different time. Firstly, at time T1, let's suppose at 11 o'clock this reaction started. Okay, that 11 o'clock is taken as T1 and this reaction went for 15 minutes. Okay, and it goes till 11:15, and now at T2 time, after 15 minutes, we are analyzing that what is the concentration of reactant and product. We represent it as R2 and P2. Okay, and delta P and delta R is the change, how much the concentration has changed of reactant and product after those 15 minutes. Clear? Now, how do we represent the rate? Now, to rate, I can say that this product amount is increasing. The quantity of product is increasing. So I can write it as rate of appearance of P, right? Appearance of P, or I can also write it as increase in the concentration of P. Okay, I will write it on the another slide. To rate, I can write increase in concentration of P upon time taken, that I can write as delta P upon delta T. And I can also write rate as decrease in concentration of reactant R upon time taken in that I can write as delta R upon delta T. Okay, so this is a way to represent increase in concentration of P upon time taken. Of course, because P concentration is increasing, the reactant is converting into the product. Okay, now as concentration of this product is increasing, so I will use a sign of plus over here, plus before this. Why? Because its concentration is increasing, and as the concentration of a reactant is decreasing, so I will use a sign of negative before this. Okay, now this is the basic part. What is the unit of rate of reaction? Units of rate, that is mole liter inverse second inverse. Okay, 1 mark question is asked from this, at what is the unit of rate? That is mole liter inverse second inverse. Okay, now how do we represent this rate in a reaction? How do we write it? Okay, we will understand that. That is when stoichiometric constants, they are not equal to 1. This is, how do we write it? See, while writing the rate of the reaction, the stoichiometric constants, they are also analyzed, they are also included. They also play a very important role. Okay, they are also included in writing the rate. Okay, so let's suppose I have this example, 2HI giving rise to H2 plus I2. Okay, now I have a question that how will I write the rate? In this case, how we will write the rate? That is equal to this 2, which is this stoichiometric constant. Okay, we will write it as 1 by 2 delta HI upon delta T. Okay, this 2, which is this stoichiometric constant, that is written in the denominator. Okay, and we will use a negative sign before this because this is the reactant. As its concentration is decreasing, so we will be using a negative sign. Okay, the same thing that we discussed over here. Okay, so here negative sign is used, and this 2 we will write it as 1 by 2. The stoichiometric constant is written in the denominator, which is equal to plus 1, because this is 1 and 1, so we need not to write that one. Okay, that is delta H2 upon delta T, which is equal to plus delta I2 upon delta T. So this is a way that we will represent this rate of reaction. Okay, so never you always have to include stoichiometric constant with that. You have to take that into consideration and always have to write that in the denominator. And negative positive sign plays a very important role. Okay, if there will be a problem with negative and positive sign, you will not be getting marks. The question will be wrong over there. Okay, so be very careful with that. Okay, this is the basics. Okay, now we will discuss about rate expression and the rate constant. Rate expression and rate constant. Okay, for that we will discuss a reaction. For example, AA plus BB is giving rise to CC plus D and D. Now C, D, this B, A, which are the small letters, they represent this stoichiometric constant. Okay, they represent stoichiometric constant. Now rate of any reaction, that is directly proportional to A to the power X and B to the power Y. Now what is this X and Y? See, at time T, T1, the reaction started. At that time, its stoichiometric constants were A and B. Now, after some time, at T2, these AB changed. And that's why to that I have written X and Y. Okay, this A and B, which are the stoichiometric constants, they can be equal to X and Y or they cannot be. X and Y may be or may not be equal to A and B. Okay, they can be equal to, suppose we are considering the reaction at T0. Okay, at that time X and Y will be equal to A and B, because at that time A and B, they have just started. Okay, so at time T0, during the initiation of the reaction, X and Y will be equal to A and B. Okay, but we are considering this rate at not at time T0. Okay, so their concentration of A and B would have changed, and this A and B would have also changed. So we are taking it as X and Y. Okay, now as I said, X and Y may be equal to A and B when we are considering at time T0, but when this reaction has proceeded, A and B concentration has changed, so their stoichiometric constants have changed. Okay, that's why I have written over here X and Y. That rate depends upon the exponents, like this stoichiometric constants, they are written in the exponents. Okay, now rate, it will be equal to K a to the power x and b to the power y. Now, to remove this sign of proportionality, we will use equal sign. Okay, for that there comes a constant. Okay, so this representing the rate in this way, when we are taking the stoichiometric constants as the exponents of the a and b, okay, and to represent the reaction in that way, that is called as rate expression. The way of writing this reaction is called as rate expression actually. And this constant that we are using over here, that is the rate constant. Okay, the k, which is the constant we are using, that is the rate constant. And the way to write this expression, okay, that is rate is equal to k a to the power x and b to the power y, where x and y, they can be equal to a and b or they cannot be, which are the stoichiometric constants. The way to write the reaction is rate expression. Okay, and x and y, they can be equal to or not be equal to a and b. Okay, so in this we have discussed rate expression and rate constant, and how stoichiometric constants they are written in the rate. Along with that, we have discussed its basics. Okay.